Great. So now we're going to continue on to section 2.2, and that continues from the frequency diagrams that we have and how we're going to graph those. And this is going to be graphed in something called a histogram. Well, with a histogram, we're going to take those intervals, and we all know that they're the same width now, right? And we're going to put them on that horizontal scale, which is our quantitative, and the heights of the bar is going to be our frequency. That's always, always, always. The frequency is always on our vertical scale. So here's an example. And we looked at these IQ scores earlier, and we have the class widths that are equal. We have the frequencies, and you can see here that these are the class boundaries. Where do we find the class boundaries? How do we find them again? We know that between 69 and 70, there's a little spot in between, and I want to find the half spot, so it would be 69.5. So that's a half between here and here, so this one would be 49.5. And then I would continue, and you can see all of those there, because those are my boundaries. Then you can see that the frequency is in fact on the vertical scale. Is this a normal distribution? It's approaching normal, isn't it? Because when I look at that, I can say, hey, it starts out low. This is really not oriented. It goes up high, and then it comes back down to below. It's far from perfect. But if I had more data, what do you think? So do you think IQ scores are normally distributed? Yeah, they are. They are normally distributed. The mean, and I'm saying now the mean being really a word that you haven't learned yet, is mu, which means the mean of a population, and the population, that's a parameter, correct? So the mean mu of IQ scores is 100. It is 100. So if you know your IQ score, which most people don't, only if you had been tested would you know your IQ score. You could look at that normal curve and know that the mean, or mu, is at 100. Relative frequency, it's really the same, except for here, instead of counting how many frequency, we have percentage, because remember, it's our relative frequency. Remember, we took 2, because there was 2 people, divided by the total number of 78 to get 2.6%, and we're showing the percent. So it still gives us the same shape, that same height of bar. And here we just go back to talking about that normal distribution has that bell shape. They increase to a maximum, then decrease, and it's basically symmetrical. There's the IQ scores. You can see it goes up and then comes back down. So the center looks like, get a different color here, looks like the center would be right about here at the top, wouldn't it? That looks about center of the curve that's superimposed. So we know it's bigger than 89.5 and it's less than 109.5, and I already told you it's right about 100, so you can see that superimposed on that. But how much variation in the data? Variation is mean how far spread out from the center is it? And that's what we're going to look at, and that's called something called standard deviation. Standard deviation. As a matter of fact, for IQ scores, the standard deviation, we've measured it to be 15. 15 points. We know that over multiple samples. If I had a curve that looked like that, I'm going to have a small variance from the center. I'm not real spread out. My standard deviation is going to be very small. Whereas I have a curve that looks like that, I have it very spread out. My standard deviation is going to be a bigger number. Okay? When I give a test, your first unit test, I'm much happier to see this than this. Much happier to see the scores being closer together. Okay? But sometimes what happens is there's something called an outlier. An outlier. An outlier can drastically pull the data. So let's give you an example of that first unit test. Let's say on that first unit test, most of you come in and your score right around that somewhere between 85, 95 area. But I have somebody who was absent from class and they didn't communicate with me, right? And if you don't communicate with me and you just don't show up for a test, I have to put a 0 in. So I have a group of students that have these scores between 85 and 95. Then I have one student down here with a 0. That student's considered to be an outlier. Imagine what that would do to my mean or my average. Okay? It drastically affects the mean. Drastically affects the mean. Also the standard deviation, because it's going to pull it out. And actually that's going to be considered skewed. Okay? Here we go, skewedness. That example that I just gave you would be considered skewed. Okay? Skewed to the right would have a positive skew and have a longer right tail. We'll draw them. Skewed to the left has a negative skewed tail. The example that I just gave you, where the test scores were all between 85 and 95, except I had one student who didn't take it and get a 0, what would happen? I'd have this long tail out here, right? And then I'd have something like this. Skewed negatively. Skewed negatively. The longer left tail. Because I've got an outlier pulling it down here. Skewed negative. Skewed to the right, a positive would have a longer right tail. So for instance, let's say that on that same test, I had a group of most of the students score between an 80 and a 90. But I gave extra credit on the test, which I've been known to do. And I had a student who scored 105. What would that do to my average? It would pull it up, wouldn't it? So on here, it would be as though I have this going on, but then I have something out here pulling it, positively skewing it, pulling it to the positive and pulling it to the right. Okay, so skewedness. So here's some shapes of distributions. The first one would be considered a normal distribution. So this would be a normal distribution. This one would be a uniform. It's almost the same all the way across, isn't it? A uniform distribution. The example I like to use for that one a lot, because we would all like to be there come December. Hawaii's temperatures year-round. every month. Do you know what they are? Same in your country. And you came here for winter? How long have you been here? But you get seasons. But here you get seasons. Here you get seasons. Yeah, yeah. But I think in Hawaii, it's between 80 is the winter and 85 is the summer. They don't even need air conditioning. Same? Maybe that should be where I retire or something. I hate winter so much. I truly do. But that would be an example of uniform. Very much an example of uniform. The one down here, I'm going up, but I'm being pulled to the right. So it's going to be positive skew. And this one, of course, is being pulled down. This is like the one that got a 0 on the test and everybody else did really well. This would be negative. Good, good. So assessing normality, there's going to be a lot of different methods that we're going to use in the course to getting that sample data from a population with a normal distribution. So when we look at a quantile plot, it can be determined if it's a normal distribution, if the points are reasonably close to a straight line. It's not a normal distribution if it's not a straight line or the points show some systematic pattern. A systematic pattern, a wave. That would really be like a quadratic function. So that would be a not normal distribution for the dots. So in a normality plot, knowing that, what do you think there? It's going to be a normal distribution because those quantile plot has almost a straight line. What do you think here? And there, of course, certainly looks like a straight line. Those would be normal distributions. Oh, wait a minute. I didn't see all those dots down here. What about this one? No, why? It looks like to me, I'm using red, looks like to me these dots are coming up here and it's going like this. That's really a logistic function. Not that you need to know that, but you can see that that would not be a normal distribution. Yeah, I didn't see all those dots there. That's it for section 2.3.